Yeah, thank you, Professor Neelima. And thank you also for giving me the chance to present here. Um, I think this ICTS is a beautiful campus. I was here last year for a talk and I got the chance to come here again. It's quite nice. And in some sense, this is the audience that I am most accustomed to from my master's days. Is it better now? Uh, can everybody hear me? Is it better? So, all right. A little higher would be better. Okay, so I'll try to talk at this pitch now. Okay, so first I was thanking the organizers for giving me this chance to present here. And I'm going to talk about climate networks as a tool for data-driven hypothesis generation. Why I say hypothesis generation is because, especially for the students here, you should not, I mean, I'm going to show several examples where we find interesting things about the weather system and atmospheric dynamics. But you should understand that climate networks was only the first step in discovering those things. Climate networks only helps us to sort of formulate new ideas about the atmospheric system. And then we have to go and test themselves independently outside of climate networks. So that part does not lie, that answer does not lie with climate networks. And this is something that maybe I'll touch upon in the very end as well to drive home that message. That's like the main take-home, high-level take-home message, that climate networks is not the answer to everything. So we've heard about climate networks already on Monday in Christina's talk. And then yesterday, Udit also talked about climate networks a lot. You have some basic idea that, okay, this is a tool that has been around for some time now, almost 2 decades. And there have been a whole bunch of studies that have used this tool for different kinds of weather and climate data sets and have done different kinds of interesting things with it. And the basic thing to understand at this point is that climate networks is, again, not limited to one particular kind of data set or one particular kind of one particular paradigm of working and approaching the data set and system. So I'm going to talk about one way of formulating climate networks today, which is based on correlation-based estimations. But you can also form climate networks from different other methods as well. To give you a brief outline of the talk, I'm going to first very briefly outline this paradigm of how I would be using climate networks. So what are, in the section, what are climate networks? I'm going to talk about how we use correlations to get climate networks. And then basically the talk is structured around 4 sort of papers, not in a chronological order. So 4 parts of the talk. So these are, the first 3 are 3 different examples of where we use climate networks for to study different aspects of the weather and climate system. Extreme rainfall, long-range connections, that's called teleconnections in weather and climate. And then one particular instance of a long-range connection between North India and Sahel, that's relatively new, and that's like something that we are working on this year. And teleconnections related to El Niños, that will be the 3rd part. So these are 3 examples. And if we have time, towards the end, I would talk about this paper where we basically looked at different ways in which you could end up with misleading conclusions from climate networks, so pitfalls of climate networks, right? But I don't know if I would manage it in time, but we'll see how it goes, all right? So what is a climate network? So think about the Earth here, and these orange dots on the planet are observation sites from where we have some information about the weather or climate system. It can be temperature measurements, rainfall measurements, pressure, humidity, you name it, right? And if you now take these measurements at each of these sites over time, you end up with what's called a time series. We've also encountered this concept already. So here are, let's say, 3 schematic cartoon time series from 3 locations, I, J, and K, in blue, green, and orange. And then, but then you actually have a whole bunch of these, maybe tens of thousands of time series spread all over the globe. What we do to get a climate network essentially is that we would use some kind of a similarity calculation. It can be correlation, We use event synchronization often for rainfall. This is something that Udit also talked about in his talk. But essentially, it can be anything. It can be correlation, mutual information, you name it. Take your favorite pick. There are many other such measures from the whole field of nonlinear time series analysis, which can give you measures of synchronization, for example. And you calculate such similarity measures between all pairs of observation locations on the globe based on the time series. And then based on some statistical test or some consideration, if it's a statistical test, it's good. But you could also have just any arbitrary consideration that you have, which is meaningful for your problem. You throw away most of the similarity measures and retain only, in some sense, the most meaningful ones or the most strongest. And then you say that, okay, whenever you have a very strong value of the similarity measure, you place an edge between those two locations, and that's represented by this Aij equals 1. Essentially, that denotes the fact that the time series at xi is somehow similar to the time series at xj. How is it similar depends on what you're using at that point, right? And you do this for all pairs, and then you end up with a network, so to speak, which exists on this geographical space, because that's where you got your data from. This is very different from, for example, what Ambika ma'am was talking about in her talk yesterday with the recurrence networks, where she then could have different ways of visualizing the same network using Gephi or something like this, because those networks exist in some kind of an abstract space in some sense. But you could do that for these networks as well, nothing stopping you, but that does not take away the fact that the nodes of these networks are essentially spatial locations. They don't have to be on the surface of the Earth, they can also be in the atmosphere. You can have different networks at different parts of the atmosphere as well, right? And that actually leads to many interesting complications with these networks as well when you're working with them. We'll come to that. And then once you have the network on your hand, then I think we've heard about this before, that you then have your entire toolbox of graph theory and complex networks at your disposal, and then you could use different ideas from these paradigms to essentially characterize the topology of your network, and by doing so, you're essentially characterizing the dynamics from where your data came from, right? So the idea is that similarity in dynamics is reflected in the topology of the network, and that should be reflected in different kinds of network measures or graph theoretical measures. And that would then help you infer something about the underlying system from where you got your data from. So if it's temperature data, it tells you something about how temperature dynamics, how temperature is advected from one region to another. Or if it's rainfall data, then maybe it tells you something about weather systems moving from one place to another, convection and whatnot. But the point is, at the end of this analysis, after you've done all this sophisticated network analysis, that's where the data analysis part ends, and you now have to really start interpreting your results. And that requires domain knowledge. You either collaborate with somebody who's an expert meteorologist or a climatologist, or as has been the case with my group a lot of times, you just read a lot of papers from climate and meteorology and then try to understand what could be the reasons that you see the things that you see in your network. All right, I hope this is clear. A few things to keep in mind. It's not a new idea to do this. Such correlation-based or similarity-based networks from time series have been used in finance and neurophysiology for a long time already. The network nodes, I said, which are the geographical locations, they are embedded in a non-trivial sort of metric space, which is the surface of the Earth. And if you think about it, given the topography and everything, it's even more complicated than being on a sphere. But we can approximately think that it's on a sphere for a lot of cases, but even that leads to somehow non-trivial results sometimes. And the definition of network edges brings in a kind of an inductive bias that it encodes essentially some assumptions about what you feel describes the processes that give rise to your data. So which similarity measures have you used, which statistical tests have we employed to decide whether to place an edge or not. These also then, every choice that you make is going to encode some assumption about the data. Why use climate networks? These are some of my reasons why I feel climate networks are useful. They uncover non-trivial spatial patterns of climate. They help you characterize in a statistical sense teleconnections, which are similarities in climate systems that have been seen already for more than half a century. They're called teleconnections. Irregularly shaped clusters in climate networks can show you regions of similar climatic behavior. It can also reveal what I would call higher order features of the climate system. Network characteristics such as degree, clustering, edge anisotropy, communities, etc., are somehow characterizing features of your data which go way beyond statistical moments like mean and variance, right? They are characterizing completely different kinds of features about your data, and that's what I would call higher order features. And they can be sometimes very useful and in discerning different patterns. And these features can also then sometimes help you validate climate models against data in a more rigorous way. So instead of looking at climate model output and looking at the mean temperature or mean rainfall all over the globe, how the map looks like, or the variance of rainfall and temperature over the globe, and how that map looks like compared to how that map looks like for data, historical data, and seeing if these two are similar and deciding that, oh, my model is fairly good, it represents the features fairly well. Instead of saying that, you could actually look at more higher order features such as degree or communities or betweenness, and then decide if your climate model is actually reproducing those topological features as well. Right, you go beyond first order characteristics. And you can separate and or group climatologies using networks, something like the Köppen-Geiger classification, which was done based on simple magnitude-based considerations of temperature, humidity, and vegetation. You could arrive at something similar based on the topology of your climate network as well. And this is something that we would do in the second example. Right, let's come to the first example, where we study extreme rainfall teleconnections all over the globe. And this is the data set. It's essentially daily data of rainfall from satellites for this time period. And these two maps basically give you a little bit of the intuition for how the data looks like. So the top plot essentially shows you the 95th percentile of rainfall. So how many millimeters of rainfall corresponds to the 95th percentile at that location. If you remove the 0 days of rainfall, this is something that Udit also did in his analysis. This is something very typical to do. Otherwise, your 95th percentile would be close to 0 because most days are non-rainfall days. Hatched regions are regions which actually do not have rainfall at all, very less rainfall, so you don't take them into the analysis. So you see that, for example, the Western Ghats is a very wet region. Here, Thailand is also a very wet region, and so on. And you see and this is based on summer months. That's why you do not see the Amazon as a wet region, if you're wondering, because that's the dry winter season in July. And based on this 95th percentile, you can now convert your rainfall series at every location into event series. And these are extreme events by the definition of the 95th percentile. Yeah. So I could try both. We could try both. If you can hear me, maybe you could increase the volume slightly, and I'll also try to speak up. And based on the 95th percentile, you can then have a time series of binary zeros and ones at every location, and every one is an extreme event. And you can count the number of extreme events that take place at every location. And this is the second plot here at the bottom. So you see this rain band of very strong, which shows large number of extreme events around the equator. And this is something that meteorologists also know. So this is just to give a feeling for the data that we work with. So we essentially have a time series at each of these locations, and we're going to construct a network out of it. And this is how it works. We use... So after you estimated the percentile, you can threshold the rainfall time series at that location based on that percentile. So if it's, let's say, 100 millimeters at Mumbai, so you have the Mumbai time series of rainfall, and you can threshold it at 100 millimeters and say that everything above 100 millimeters, everything above the 95th percentile is an extreme event. That's a 1. And everything else is 0. So you have a binary series, and you essentially then count the number of ones. That's this number here. This is TRIM, the Tropical Rainfall Measurement Mission, which later on became something called the Global Precipitation Mission. It's a fairly well-established satellite data for precipitation. So this is, as I said, when I was making that point about the Amazon being dry, so this is 95th percentile only for the summer months. So as in, you mean the number of time points? That will be what? So it's four months per year. So that's 120, let's say, times 18 years. Yeah. Is it? Oh, sorry, it's 3 months per year. It's 3 months, yeah. So 90 times 18. All right, then we use event synchronization. Zooming into the Indian region just as a cartoon to see. So if you have two rainfall time series from these two locations, you can then threshold them, as I said, using the 95th percentile or 99th percentile, and then you get event series like this. And then you essentially, event synchronization is a fancy way of counting numbers. So you set up a small tolerance window in this, which is shown by this gray rectangle here. And you say that, okay, within this tolerance window, do I have coinciding events in both time series? And you just count that. And you just do this counting for all pairs. And then you have your event synchronization count, so to speak. And once you have those counts for all possible pairs, you do statistical tests, which will decide whether you place an edge between those two locations or not. The first test that we do is to test if the event synchronization counts that we get are significant with respect to a null distribution of simply randomly shuffling the event synchronization, the event series at each location. Yeah. And then based on this, so you would do this random shuffling for all pairs where you have an event synchronization count, and then you would get a null distribution of events, and you can basically then calculate event synchronization counts for each of those randomizations. And then that gives you a null distribution, a random distribution of 2000 event synchronization values in this case. And you place an edge between I and j if the actual observed event synchronization count is higher than is the 95th percentile or 99th percentile in this case of that null distribution, right? But there are some issues with doing only this first test. First is that it does not, it leads to this problem of multiple comparisons, which happens when you're doing many statistical tests at once. And if you think about it, we are doing a statistical test, this 2000 random event synchronization values that we get for every pair. And then we have, like, I don't know, 10,000 combination 2 pairs. So we are doing so many statistical tests at the same time and trying to interpret the results of all these statistical tests at the same time. And that leads to the problem of multiple comparisons, especially in such large data sets. And there are methods to correct for this, but these are very classical statistical methods from, I don't know, 50s and 60s. And they are not really designed to deal with such a high number of tests at the same time. They're probably designed to maybe for a few hundred, or is already probably a large number of statistical tests for these methods. So we need to incorporate more assumptions and maybe come up with a new, slightly more sophisticated statistical model for which will allow us to really weed out the random event synchronization values that we get. So the whole fear in this case, what we are trying to avoid here is to get high event synchronization values that could have come about just by randomness. That is what we're trying to avoid. We don't want to place an edge between two locations where, in fact, those two locations, the edge could have come about just by random chance. If that random chance is high, we want to avoid such a case, right? So what do we do here? We got an idea when we were looking at this plot. This is something which is we often looked at in the case of climate networks. It's called a link length distribution. What it essentially shows is that once you've constructed your climate network, every edge in that climate network between two locations has you can associate a geographical length to that edge, right? Not a length on the network itself, but the real geographical edge length between those two locations on the Earth, right? And then you can sort of get the geographical length for all the edges in your network, all the links in your network, and then you can create a histogram. And this is that histogram. The circles are essentially that link length histogram from the climate network that we construct. And the black line here, the black line is a similar link length histogram or distribution from just randomly distributing as many edges between those nodes. So if we had, let's say, a million edges in our network, and those million edges give us this link length distribution, the black line essentially is the link length distribution for a network where we distributed those million edges randomly, right? And that essentially follows the cosine law of the sphere, basically, the great circle distances. Yes?
Not synchronization anywhere yet, right?
Yeah, so event synchronization, it's a kind of a, so it came, yeah.
Now it's working.
So it's just a name, event synchronization for us. It's just a name. At the end of the day, it's just a statistical measure that we're using. It does not really have anything to do with synchronization as we understand, although it came from that domain, so to speak, the idea, the core idea. But in this avatar, it's just a statistical measure for us. Right. So this bump is interesting because what it essentially tells us is after this length, this part of the distribution completely overlaps with the distribution of the purely random network, which means that, and this is a kind of a peculiar problem, when we construct climate networks, we are at some level very deeply interested in these kind of long-range teleconnections. I mean, nearby similarities in climate, that's not so interesting. The long-range surprising similarities in the climate system is what interests us. But what this distribution essentially tells us is that the long links in your climate network are statistically indistinguishable from random links if you don't do any additional test. Right? And that's a problem. And so we thought about how to get around this, and essentially then we came up with a second statistical test, which is now a little bit more spatial. We thought about coming up with something that tells us the significance of edges with respect to every location on the globe. And what we did was that we loop over all the nodes in the network, and for every node, if it has, I don't know, 1,000 edges, we randomly distribute those edges from that node, those 1,000 edges. And if some other node has 100 edges, we randomly distribute those edges. So we essentially create a kind of a null model for every node. And we do that several times. And then we can see where each of those edges end up, and we can smooth that out using a Gaussian KDE, and basically that gives us a background spatial distribution of where edges end up from all nodes, given the current degree distribution of the network, right? And then we can look at the actual observed edges of the network and see if they sort of stand out against this background of network edges that we distributed all over the place, right? So the key idea here was that, and this is something that occurred to us if you also think about the first picture that I showed with this nice visualization of the globe and those orange links. Most of the time in climate, the links tend to bundle together in space. And we essentially wanted to come up with, so post facto, we essentially wanted to come up with a test that would statistically tell us where we have statistically significant bundling happening. We wanted to extract those bundles, and these would be then interpreted as something that is not randomly likely and physically meaningful, therefore. Right, and it works. So, for example, this is a small intuition how that works. So we consider this red point here in North India, and these are all the edges that come up from this point after the end of the first statistical test, just the random shuffling of the event series, right? And then we do the second statistical test where we randomly rewire these edges to everywhere else on the globe. And then what we get is, oops, sorry. No, I messed up. Then what we get is that, ignore this orange circle for now, we get these kind of link bundles. These link bundles then stand out of the spatial random model that we created, which tells us that, okay, this bundling that is occurring between these two regions or these two regions is somehow statistically significant and therefore might be physically meaningful. Okay, it's still, there's no 100% guarantees here. All right. I messed up with the order. So this was supposed to come after that. So, but how do we know that there are still artifacts, right? We don't, and that's why now we have to put an end to the statistical analysis, the data analysis part, and we actually have to dig into the literature and go over everything on a case-by-case basis. And in this paper, what we did was we zoomed on into this one. I mean, we actually did more, but the narrative is such that in the paper that we now just zoom into this one particular link bundle, which, if you see here, it's between some regions in Southern Europe to this region in India. And then after looking at many different variables for many different plots, we were able to find that climatologists already know this kind of connection between Europe and what we are calling South Central Asia or North India, which is explained by something called the Silk Road pattern. Essentially, it's a movement of air, it's a wave of air that occurs in the really upper troposphere at around 200 hectopascals height, pressure level. And that sort of, this is a wave train where this is, the bottom plot is, so the upper plot is rainfall at day 0. So you can essentially count those days where you have the maximum synchronization, considering on time season. And day 0, you see you have a lot of rainfall in Europe and none over India in this box, but after 3 days, you have a lot of rainfall over India and none over Europe. That's essentially because on the bottom plot, what we see is what's called the V wind, so the longitudinal wind, which is positive. Red means northward winds and blue means southward winds. So if you have alternating blobs of red and blue, essentially it means that you have a wave, right? Because this part is the positive wind, the red blob, and then this part is the negative wind. That means you have a wave train. And these V wind plots are from 250 hectopascals upper atmosphere. So that wave train, and this is something that has been there in the literature for several decades now, and we use this anecdotal result as evidence that, okay, at least for that particular blob between Europe and North India, the result was not an artifact. And that's one core message that I would like to drive home, is that no matter what statistical test you do, no matter how many statistical tests you do, there's always the risk of there being artifacts in your results. So you have to go back and come up with plausible mechanisms and explanations, plausible explanations that tell you, okay, there is something going on in the weather system or in the climate system that explains what you've seen, and then you can rule that out. So now we can essentially... This is not really, no, Spain would be here. That's the Iberian Peninsula. So this would be more northern Italy, Switzerland, eastern France. Yeah. So around the Alps a little bit. I don't know what's the Julian Alps. Okay, could be. Yeah. Yeah. Oh, artifact is artifact essentially is, let me just go to this one. Artifact is something that, let's say, I see some connection between this and this, but there is a lot of physics telling us that essentially all fluid dynamics in the southern hemisphere, most of the time, tends to remain in the southern hemispheres. Like circulatory systems from the southern hemisphere do not cross the equator into the northern hemisphere. So then all these blobs that we see to the southern hemisphere might be an artifact because there is no physical mechanism to really explain that. Or maybe that's just some common driver or something like that. that something is making this happen at the same time as this happened. I don't know, something from the sun or somewhere else that has more like a global influence. But an artifact essentially is something that you see as meaningful from the end of your statistical analysis, but most likely does not have any physical or whatever. If it's a chemical system, biological, whatever, it does not have, I would not use the word real, but does not have a plausible mechanism in whatever domain you're talking. Yeah. June, July, August. So this is the northern summer season, boreal summer season, northern hemisphere summer season. Okay, so now what about the rest of the regions? Yeah, essentially you have to do that. You have to go through each of them on a case-by-case basis and dig deeper. We did that at least in part. I'll come to that in the next part. So pit stop, event synchronization allowed us to create climate networks from extreme rainfall series. And here we used some assumptions, inductive bias to include, to detect more quote unquote physically meaningful teleconnection bundles. And then we had to go back to domain knowledge and identify plausible mechanisms, right? And then in the next part, I think I'm just going to do two parts then today because I was a bit slow. We investigated this connection from the India to the Sahel. Similar data set, and this is a paper that's in progress. It's almost accepted, should be out in a few months. But now we focus only in this region. We don't take global data. We just focus only on this region because we know that we want to look into this deeper into this connection between India and the Sahel. Again, we have rainfall data sets from these regions. We threshold them, event synchronization, adjacency matrix. But now what we do is we look at communities in the network, and that's done by this method called stochastic block models that essentially corresponds to rearranging rows and columns in your adjacency matrix till you get such block-like structure. That's a very computationally intensive problem. That's why you need smart methods like stochastic block model. And that gives us communities. So these kind of blocks are communities in the network, and these communities would correspond to geographical regions from where your data came from. If we zoom in, you see that, okay, this light blue community, I mean, there are some data points here as well, but what we're interested here is that India, the Sahel region, and northern China, they are all in this one community. The connection to India and China were explored in some other papers by other groups. We did not bother about that, but so we thought that this was something new. We asked a few people. They also said that they don't really know why they should be in the same community, so we dug deeper into that. This is another way of quantifying the community. We come up with something called the membership likelihood of belonging to that community. And that shows that, okay, these three regions belong to the same community. And here in this plot, you see lead lag correlations between an average rainfall time series here over this community, this subcommunity, subgraph, an average time series here and an average time series here. And if you do lead lag correlations, you find that the India community leads the East Asia, the China community by 3 days, and the Sahel community by around 12 days. And the green curve, that's what we are more interested in. And these are just some other ways of characterizing what's going on there. The most synchronous days, these MSDs, that's also shown here as yearly averages. Most synchronous days are defined as days where you see the highest number of synchronous rainfall events between these two regions. They seem to occur mostly in July and August. So even though we do consider June, July, August, and September initially as our monsoon season, but actually the core phenomenon occurs just in June and July. To extract sort of more signal out of the data, what we do is we estimate these most synchronous days and cluster the timestamps of these most synchronous days. So the assumption here is that we say, okay, the most synchronous days are all not the same. So there would be some noise even in these most synchronous days. So because you see that, okay, even these most synchronous days actually sometimes have, they have some distribution here. So you take those most synchronous days and you cluster them based on, again, some climatological variables. In this case, we looked at wind fields at the mid-troposphere, because after a lot of digging around, that seemed to be the most meaningful. And we do the clustering using EOF. So we take wind data we lat long wind data over time, and then we first average them along one dimension. So we reduce one dimension of the data, and then we do EOFs on this. And in the EOF space, we do clustering, because EOFs essentially reduces the dimension, allows us to reduce the dimensionality of the problem and make the clustering more tractable. And that gives us two clusters. And these two clusters showed essentially one cluster corresponds to there being even stronger synchronization than normal, and the other cluster corresponds to weaker synchronization. And that's the one that we don't worry about so much. And these are different weather variables, meteorological variables corresponding to these clusters. So the strong synchronization cluster, if you, again, because we are clustering timestamps, right? So we can take the timestamps of the strong synchronization cluster and average sea surface temperature on those timestamps. And that's what this pattern looks like, and it's essentially a La Nina-like pattern. So that gives us an indication that the synchronization that we see between North India and the Sahel, on the strongest synchronization days, it's something to do with a La Nina kind of situation in the Pacific, right? If you look at, again, upper troposphere winds, this is the horizontal, like latitudinal wind. So brown essentially means winds which are blowing towards the west. Purple means winds which are blowing towards the east. You see that on those strong synchronous days, you have this strong band of winds blowing towards the west. This is something called, which is known again to climatologists, called the tropical easterly jet. And that's sort of enhanced on those strong synchronization days. And there's also weakened vapor transport. That's again another meteorological quantity that was useful in formulating a mechanism about what could explain the synchronization pattern that we see. Right? And looking at all of this, we essentially could hypothesize about some mechanism that could give rise to the synchronization, and which goes something like this. We need background La Nina-like conditions. Then we need a favorable phase of the monsoon intraseasonal oscillation. Intraseasonal oscillation is the thing which gives you the active days, active phases, and break phases within a particular monsoon season. A monsoon season, even if you have a strong monsoon year, it's not uniform from June to August. You have periods, like you have a couple of weeks of active monsoon, couple of weeks of break monsoon, and so on. And that's called active and break phases, and that corresponds to what's called an intraseasonal oscillation of the monsoon. So we need a favorable phase of the intraseasonal oscillation. We need an enhanced tropical easterly jet. This was the brown colored winds in the previous slide. And this favorable phase of the monsoon leads to strong convection over North India. That creates rising air in the troposphere. This disturbance reaches up to the level of the tropical easterly jet and then travels along the easterly jet as a wave disturbance. Reaches the Ethiopian highlands, and that leads to convection there. And then after around 10 days, you have convection over the African region, the Sahel region. And then we could sort of look at more plots, more variables to sort of motivate that, okay, this is a plausible mechanism. Huh?
All the factors. The next slide.
The next slide, this one, yeah, okay. Yeah.
So once again, if you don't.
So the first point, La Nina-like conditions is the colder temperatures in the Pacific. And then a favorable phase of the monsoon is essentially a particular subset of the summer season where you have intense rainfall. So that second point is more or less similar, correlated to the fourth point here. That second point leads to the fourth point, that you have abnormally strong convection, strong rainfall over North India. And this strong rainfall over North India creates rising air that reach the upper troposphere. And you have already an enhanced tropical easterly jet. So this corresponds to one of those years where the tropical easterly jet also is enhanced. So that's a background condition. And the disturbance, the rising air that goes up to the tropical easterly jet, that then creates a wave on the, so the jet is like a flow which acts as a waveguide where the disturbance can travel. And if you see, the jet is positioned like this. So the wave will now travel along the jet and reach this part, Ethiopia and this one. And there, essentially, that disturbance causes more air to rise up from below. I mean, it probably tries to cause air to rise up from below along the way as well, but then you have the desert there, so that nothing happens there, right? And that air rising up from below is again creating another wave on a jet that stays below the African easterly jet over the Sahel region, called the African easterly jet. And the African easterly jet is typically responsible for rainfall over that region. So one wave disturbance on the tropical easterly jet somehow leads to another wave disturbance on the African easterly jet, and the second disturbance over the African easterly jet causes rainfall over the region. So it's like a whole cascade of events that happens. I mean, this is still a hypothesis, and we've just come up with some meteorological plots to sort of provide evidence for this. A true test would be, if you have a atmospheric model with Navier-Stokes equations, and then you could sort of perturb with these things, set the favorable conditions, and have also unfavorable conditions, and look if this hypothesis is really true. And that is something that we've not done. Yeah, could be that. So one of the reviewers said that the tropical easterly jet is not necessary. T.
Descends near somewhere Madagascar, not Ethiopian island. That's what literature says. Again, the African easterly jet you are saying, it does not originate from where TJ descends.
No, it doesn't have to.
Yes, so that's also how it is related.
So the thing is, these are also again not the typical conditions for TEJ and AEJ. These are special years, like this is enhanced TEJ, and the African easterly jet is not enhanced. But you see that, for example, here in this case, the tropical easterly jet does not, on these particular days, it does not really descend over Madagascar. So you're right in a sense, but that is again a climatological statement. But this is not really a climatological statement in that sense, because that is like, you've taken average over 30 years of summer or something like this. But this is like taking average only on those days where we see synchronization over India, and taking, it's a climatology over a very much smaller, finely selected set of days. Extreme events, because our whole starting point was extreme events, extreme rainfall, right? And then we have extreme rainfall over India being synchronized to extreme rainfall over the Sahel. It's a specific geography. It's this region here. This region here. Do you see this red boundary? That turns out to be a community, a geographically bounded region in our climate network. And then we can average the event time series in this community. And then we get something which, like this kind of a time series, where you have a number of most synchronous days on the y-axis, and then we can look at the most synchronous days here, like you can threshold this and look at really those days where you have really a high number of synchronous. So basically you have widespread extreme events over, and only on those days do we sort of get average the zonal winds to get this climatology. So this is a very different kind of climatology from the typical climatology that people would study for TEJ. That is what makes things different when you approach meteorology from the climate networks perspective, that it allows you to select a kind of a different set of days, which probably digs deeper into and finds out more smaller phenomena that would not otherwise would have been hidden in the overall climatology, maybe averaged out or something. The data is the TRIM GPM data, so it's from 98 till, I think we chose not till 24, but I think 22 or something. It's for the last 2 decades roughly. All right, I think I should end after this. I just had maybe the desire to show one. How do I do this? Let's skip everything and just go to the last slide. Okay, this is a summary. We talked about knowledge discovery with climate networks, and climate networks are useful to generate data-driven hypotheses. This is actually not so important, but what I talk about. This work, of course, has been done with a lot of people together. So Nicholas and Alyosha, they're really good friends. We did our PhDs together and have been collaborating ever since. Jürgen Kos was my doctoral supervisor. Ulrika Luxburg and Martin Bose are our computer science department people at Tübingen. The rainfall Sahel connection that we just looked, that's Felix's work. And there was some other stuff from Jakob as well, which I did not get to show. And also very nice master's and bachelor students. I want to show this. So this is my understanding of how climate data analysis works. So you spend most of the time reading papers. I hope the handwriting is legible. All right, that's it. Thank you.
Okay, so once you have established these teleconnections, does that mean that in two places which are connected, rain will come simultaneously? Or can we say that if it starts in this place, it's going to start next in the other?
The definition of the edge says that rain should come simultaneously. The definition of the edge is such that the rain should come simultaneously. But in an average sense, because we've counted over the whole time period, right? The counting involves the whole time series. So in an average sense, these two places show simultaneous rainfall, extreme rainfall. No. High performance computing. Like you have big data sets, the correlation matrix is huge, millions of entries. You cannot do it on your computer. Laptop doesn't work. Yeah, of course, yeah. We have to use the cluster. You cannot. I mean, the correlation matrix is really huge, right? I mean, at some point, I think in one of the slides it said there were 500,000 nodes. So that's like 10 to the power 6 nodes, and then you can imagine how many edges and so on. So the correlation matrix is really huge.
So the satellite images data, the data that I had worked on, so the satellite gives the data for 7 days gap.
Oh, this is not like that. It's satellite data, but it's processed satellite data in the sense that there are scientists in the US who are part of this project who've taken those satellite images, those radar images, and used the proper calculations necessary to translate those, what do you call it, the reflectances
I see.
From the precipitation radars into millimeters per hour kind of values. And then they also have some way of interpolating, some fancy way of interpolating that they finally release what's called a rainfall data product that is gridded, uniform in space, uniform in time. So we don't, like those raw data sets, they don't work with that.
Okay.